All right, in this video, we're going to do some more advanced examples of what we talked about last time with the superposition principle for um, undetermined coefficients. So let's go ahead and look at number 7 from the book. And we have y double prime plus 3y equals negative 48x squared e to the 3x. So what we see is that our auxiliary equation will be m squared plus 3 is equal to 0. So m squared will be equal to a negative 3, making m equal to plus or minus root 3i. That's a 0 plus or minus root 3i. So our yc is going to be e to the 0 is 1, c1 cosine of root 3x plus c2 sine of root 3x. And now we're going to pick a yp that could give us this form. So I see a quadratic times an exponential. So I'm going to pick ax squared plus bx plus c times e to the 3x. Yp prime is going to be 2ax plus b e to the 3x plus 3e to the 3x times ax squared plus bx plus c. That's my product rule. So when I add the pieces parts together, I get e to the 3x on the outside here. And I have 2ax plus b plus 3ax squared plus 3bx plus 3c. So let's write that now in descending order of exponents. So I have 3ax squared plus 2a plus 3bx plus b plus 3c. And that is e to the 3x on the outside there. So yp double prime is going to be derivative of the first part, leaving the second part alone. 6ax plus 2a plus 3b e to the 3x plus 3e to the 3x times 3ax squared plus 2a plus 3bx plus b plus 3c that. So yp double prime is equal to 6ax plus 2a plus 3b plus 9ax squared plus 6ax plus 9bx plus 3b plus 9c e to the 3x. Combine my like terms and write in descending order. So I have 9ax squared plus, and then my 6ax, and my 6ax is 12ax, 9bx, And then I have 2a plus 3b, and 3b is 6b plus 9c e to the 3x. So now I want yp double prime plus 3yp, and that needs to be equal to a negative 48x squared e to the 3x. This looks really messy, but you're going to see a bunch of stuff is going to drop out here in a second. So original part here, 9a x squared e to the 3x plus 12a plus 9b x e to the 3x plus 2a plus 6b plus 9c e to the 3x plus 3 times my original is 3a x squared e to the 3x plus 3b x e to the 3x plus 3c e to the 3x needs to be equal to a negative 48x squared e to the 3x. Combine my like terms. 9 and 3 is 12a x squared e to the 3x plus 12a and 9b x e to the 3x. We have another 3b, so that's 12a plus 12b x e to the 3x plus, and then we have 2a plus 6b plus another 3c. There will be 12 c. So that is 6b plus 12c e to the 3x needs to be equal to a negative 48x squared e to the 3x. So now we have 12a x squared needs to be equal to a negative 48 x squared e to the 3x, and a needs to be negative 4. 12 times negative 4 plus 12b is equal to 0. Negative 48 plus 12b equals 0, so 12b equals 48, and b equals 4. 2a plus 6b plus 12c also equals 0. A is negative 4, so that's negative 8 plus 6 times 4, that's 24, plus 12c equals 0. 16 plus 12c equals 0, so 12c equals negative 16, and c is going to be equal to a negative 4/3. So my yp is going to be a negative 4x squared plus 4x minus 4/3 e to the 3x, making my total y here equal to c1 cosine of root 3x plus c2 sine of root 3x plus a negative 4x squared plus 4x minus 4/3 e to the 3x. Let's move on to the next problem. It looks a little deceptively simple here. Y double prime minus y prime equals negative 3. So let's start off with our auxiliary equation, and we'll discover what the problem is here shortly. m equals 0, or m minus 1 equals 0 equals 1. So my yc equals c1 e to the 0 is just c1 plus c2 e to the 1x is x. So my problem is that I would normally guess yp is equal to a, but I can't guess that because that's the same thing as c1. So I'm going to have to take it up a degree to make it yp equals ax. So that makes yp prime equal to a and yp double prime equal to 0. So yp double prime minus yp prime equals 0 plus a, and that needs to be -3. Sorry, this is a minus sign. Minus a equals a -3, so negative a equals -3, and a equals 3. If a is 3, then y, which is equal to yc plus yp, is equal to c1 plus c2 e to the x plus 3x. All right. So when your guess for yp already exists in yc, you have to go up however many degrees you need to, multiplier of x to the n, in order to get a version of that solution with the repeated root rule that isn't already in your YC. So let's go ahead and let's look at the next problem, and that'll be the last one for this video. It's going to be quite lengthy here. So y double prime minus y prime plus 1/4 y is equal to 3 plus e to the x over 2. So let's look for our particular or our complementary solution first. With our auxiliary equation, we end up with m minus 1/2 squared equals 0. So m minus 1/2 equals 0. M equals 1/2 with a multiplicity of 2. So my yc is going to be equal to c1 e to the x over 2 plus c2 x e to the x over 2. On the right-hand side, I see an e to the x over 2. So I'm going to have to go all the way up to x squared e to the x over 2 and my yp, my guess for yp, but I also have this constant which doesn't show up anywhere in yc. So I just have a plus b x squared e to the x over 2. I take the derivative of yp, I get 2b x e to the x over 2 plus b over 2x squared e to the x over 2. That is 1/2 bx squared plus 2bx e to the x over 2. So yp double prime is equal to bx plus 2b e to the x over 2 plus half of that is 1/4 bx squared plus bx e to the x over 2. Combine those like terms and I get 1/4 bx squared. Bx and bx makes 2bx and 2b e to the x over 2. Now I need to have yp double prime minus y prime, yp prime, plus 1/4 yp, and that needs to be equal to 3 plus e to the x over 2. So this is 1/4 bx squared plus 2bx plus 2b e to the x over 2 minus, and then this is yp prime is 1/2 bx squared plus 2bx e to the x over 2, and then plus 1/4 of a plus bx squared e to the x over 2. And that needs to be equal to 3 plus e to the x over 2. So looking at our parts that are alike here, we have 1/4 minus 1/2 plus 1 bx squared e to the x over 2 plus 2b minus 2b x e to the x over 2 plus 2b e to the x over 2. And then plus 1/4 a, and that needs to be equal to 3 plus e to the x over 2. So all of this 1/4 plus, should be another quarter here, sorry, 1/4 of this and 1/4 of that. So 1/4 a, there we go, yes. So 1/4 and 1/4 is 1/2, and 1/2 minus 1/2 is 0, so that all zeroes out. 2b minus 2b, that zeroes out as well, leaving me with 1/4 a plus 2b e to the x over 2 is equal to 3 plus e to the x over 2. So 1/4 a is equal to 3, making a equal to 12, and 2b is equal to 1, making b equal to 1/2. So now that makes my yp equal to 12 plus 1/2 x squared e to the x over 2. And my total y is going to be my yc, which was c1 e to the x over 2 plus c2x e to the x over 2 plus my yp, which is 12 plus 1/2 x squared e to the x over 2. That'll be my last one for this video. We'll come back next time and do a part 3 of this, where we talk about the right-hand side containing trig functions in the form of sine of alpha x, cosine of alpha x, or sums of those as well. Maybe even those things multiplied by some polynomials or exponential functions along with it. We'll see if we can get to some of those, but I definitely want to show you how we need to treat sine and cosine a little bit differently because the derivative of cosine turns into a sine function, the derivative of sine turns into a cosine function. So we always have to have both pieces at play in our guess for our particular solution when we see either sine or cosine on the right-hand side of the equation. So more on that next time when we come back for part 3 of the superposition principle for undetermined coefficients. See you next time.